What if I told you that the computer you're using right now is lying to you, not because it's broken, but because reality itself has a loophole? Here's the strange part. I found that loophole, not in a dream, not in a thought experiment, but in the cold, uncomfortable math that lives underneath everything you think is solid and real. And the loophole doesn't just change computers, it changes what it means to know anything at all. So let me ask you something nobody asks out loud. What if the universe isn't computing the world the way we assumed? What if it's doing something far weirder, far more beautiful, and far more terrifying than any machine we've ever built? I want you to sit with that question for a moment. Don't try to answer it. Don't reach for an explanation. Just let it be strange for a second. Because that discomfort you might be feeling right now, that subtle vertigo of not being sure what the ground is made of, that is the correct response to quantum mechanics. That's not confusion. I played bongo drums in strip clubs in Pasadena, taught myself to crack safes, and spent the better part of 6 decades trying to understand why the universe behaves the way it does at the very smallest scales, and failing beautifully, repeatedly, in ways that kept me awake at night with something that felt a lot like joy. But I'm not here to impress you. I'm here because there is something, one specific idea, that I spent the last years of my working life obsessed with, and I believe it might be one of the most important ideas in human history. Not because it makes computers faster, not because it will eventually break encryption and terrify governments, though it will. I believe it's important because of what it says about the nature of reality, about what knowledge is, about what it means to live inside an uncertain universe and still manage to understand something true about it. That idea is the quantum computer, and I want to tell you what it actually is. Not the version with the shiny graphics and the buzzwords. The real version. The version that starts with a crisis, moves through a revolution, and ends with a kind of peace that I don't think any purely classical way of thinking could ever offer. So here is what I want to give you today. I want to give you the reason classical computers hit a wall that no amount of money, no amount of transistors, no amount of clever engineering could ever knock down. I want to give you the three principles: superposition, entanglement, and interference, not as vocabulary words, but as genuine ways of being that the universe uses, and that we, if we're paying attention, can learn something from. I want to bust open the most common misconception about quantum computers, which is the idea that they're just faster. They are not faster. They are different in the way that a conversation is different from a monologue. They are different in the way that asking the universe a question in its own language is different from demanding it translate itself into ours. And I want to give you something practical, something you can carry out of this conversation and into your actual life on an actual Tuesday. Because the principles that make quantum computing work are not just engineering principles. They are, I think, principles for how to live more honestly inside a genuinely uncertain world. But we're going to start where all good stories start, with a catastrophe. The catastrophe happened in the late 1800s, and the people living through it didn't know it was a catastrophe. That's the thing about the moments right before revolution. They look, from the inside, like success. Physics at the end of the 19th century was a triumphant enterprise. Newton's laws described the motion of planets with such precision that you could predict where Jupiter would be in 1,000 years and be right. Maxwell had unified electricity and magnetism into a single elegant theory. Thermodynamics had explained heat and energy and why engines work. There was a general feeling among physicists, an intoxicating, dangerous, wonderful feeling, that they were nearly done, that the big questions had been answered, that what remained was filling in the details. Lord Kelvin, one of the most brilliant physicists of the age, gave a famous speech in which he said, essentially, that physics was complete, that there were only two small dark clouds on the horizon, two little puzzles, two minor loose ends. Those two loose ends were the ultraviolet catastrophe and the photoelectric effect, and from those two clouds came quantum mechanics, the theory of relativity, and the complete demolition of everything Kelvin thought he understood. History does have a sense of humor. It's just usually a very unsettling one. I want you to imagine for a moment what it felt like to be a physicist at the end of the 19th century. You have this beautiful, seamless picture of the universe. Everything is continuous. Everything flows. Space is like an infinite smooth ocean. Energy is like water. You can have any amount of it, any fraction of it. It moves in continuous waves from one thing to another, There are no gaps, no jumps, no sudden transitions. The universe is analog. In the way that a dimmer switch is analog, you can turn the light to any level, any degree of brightness, infinitely variable, perfectly smooth. Now imagine someone comes to you and says, I've been doing the calculations. The math says that if you heat up a metal until it glows, which we all do, which we observe every day, the amount of energy it should radiate at high frequencies should be infinite. The math predicts infinite energy from an ordinary hot piece of metal, which is, as we might gently note, not what we observe. What we observe is that hot metals glow red, then orange, then white, and then they stop putting out energy at the highest frequencies. The energy doesn't go infinite, it tails off. The universe, as always, refuses to be as dramatic as the math suggests it ought to be. So, there's a discrepancy. The theory predicts infinity. The universe produces something finite and sensible. And a man named Max Planck, in the year 1900, sat down to fix this discrepancy. He wasn't trying to start a revolution. He was genuinely just trying to make the numbers work out. He was that kind of careful, methodical physicist who likes his equations to agree with experiment, not because he's unimaginative, but because he had deep respect for what reality was actually doing. And here is what Planck discovered, entirely against his will, and to his considerable personal distress. The only way to make the equations agree with what we observe is to assume that energy doesn't come in a continuous flow. Energy comes in discrete packets, minimum units, indivisible chunks. He called these chunks quanta, and he was fairly horrified by this. He spent years trying to find a way to get rid of the quanta and return to the comfortable continuum. He couldn't, because the universe had decided, with or without Max Planck's blessing, that this is how it works. I want you to really feel what this means, because I think we've been hearing about it for so long that the strangeness has worn off, and the strangeness is the whole point. Imagine you're a seamstress. You work with thread. Thread is the paradigmatic continuous thing. You can cut it at any length, any fraction of an inch, any infinitesimally small portion. That's what makes thread useful. It's continuity. Now imagine you discover, after years of working with thread, that there is a smallest bead, that you cannot have half a bead, that you cannot have 1.7 beads, that between one bead and the next bead there is nothing, no gradation, no transition, no in-between. Reality comes in minimum packages. This is what Planck found, and the implication, the shattering, civilization reshaping implication, is that the universe, at its smallest scale, is not continuous, it is granular, it is discrete, it comes in pieces. And every single assumption we had built about how nature works, every elegant equation, every beautiful theory, rested on the idea that it didn't. Now I want to pause here and say something that I think gets lost in the telling of this story. Planck's discovery didn't make him feel triumphant. It made him feel like he'd found a problem he couldn't solve. He referred to his own equation, the one that worked, the one that matched experiment perfectly, as a mathematical trick. He didn't think it was literally true. He thought he had found a clever fiction that happened to produce correct answers, and that someone would eventually come along and replace it with a real explanation, a comfortable one, a continuous one. That someone never came, because what Planck had found wasn't a mathematical trick. It was a window into the actual structure of reality. And once you look through that window, you can't pretend you didn't. You can't unsee the beads on the thread. Albert Einstein looked through the window in 1905 and said something even more radical. He said not only does energy come in packets, light itself comes in packets. Individual, indivisible particles of light, which he called photons. And he used this idea to explain the photoelectric effect, the other dark cloud, in a way that was so clean, so perfectly matched to experiment, that it eventually won him the Nobel Prize. The same Einstein who later spent decades trying to prove that quantum mechanics was wrong. The universe has a way of trapping you with your own insights. And so, by the 1920s, there was a revolution underway. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and a chorus of brilliant young minds were assembling the theoretical framework that would eventually become quantum mechanics. And quantum mechanics said things that were mathematically precise and experimentally confirmed and utterly irreducibly philosophically bizarre. It said that particles don't have definite positions or definite velocities until they're measured. That a particle's location is, before measurement, a spread out cloud of probability, a wave function, describing not where the particle is, but where it might be, with what likelihood. It said that the act of measuring a particle changes it irrevocably, that you cannot observe nature at the quantum level without disturbing it, that there are pairs of properties, position and momentum, energy and time, that cannot both be known precisely simultaneously, not because our instruments are imprecise, because nature itself has built imprecision into its deepest level. This is Heisenberg's uncertainty principle, and it is one of the most misunderstood ideas in all of science. People hear uncertainty principle and they think it means our measurements are uncertain. They think it means we need better instruments. No. It means the universe itself is uncertain. It means a particle genuinely does not have a definite position and a definite momentum at the same time. Asking for both is not a measurement problem. It is a category error. It is like asking for the color of a sound. The question doesn't connect to what the universe is doing. I remember being a student and encountering this for the first time. I remember the specific quality of the confusion it produced. Not the ordinary confusion of not understanding an explanation, but the deeper confusion of understanding the explanation perfectly and still not being able to believe it. The mathematics was clear. The experiments confirmed it. And yet, something in my brain kept reaching for the comfortable story underneath. Kept asking, yes, but where is the particle really? What is it actually doing when we're not looking? And the honest answer, the answer that quantum mechanics gives, and that every serious attempt to find a better answer has only confirmed, is there is no really. The particle's properties do not exist in a definite form before measurement. What exists is a superposition of possibilities, a mathematical object called a wave function that contains in encoded form all the possible states the particle could be in, weighted by probability. And when we measure it, the wave function collapses. One possibility becomes actual, the others vanish, and which possibility becomes actual is, within the constraints of probability, genuinely random. Not pseudo-random, not deterministic, but complicated. Genuinely, irreducibly, fundamentally random. Einstein hated this. He famously said that God does not play dice with the universe, and bore with the gentle patience of a man who has heard this objection many times, reportedly replied, "Stop telling God what to do." I find both of them sympathetic. Einstein's discomfort came from a profound aesthetic commitment to a universe that makes sense in the way physics had always made sense, where causes have effects, where knowing the initial conditions tells you the final state, where there is, underneath all the complexity, a clean deterministic engine driving everything. It's a beautiful vision. It's just not the vision the universe chose. And Bohr's reply, for all its sharpness, contains something important. The universe is not obligated to satisfy our aesthetic preferences. It is only obligated to exist, and it exists at the quantum level, in a way that resists every comfortable story we try to tell about it. I spent a lot of time with this, a lot of time, and I'll tell you what I arrived at, not as a conclusion, not as a satisfying resolution, but as a kind of working piece. The universe at the quantum level is not broken. We are not missing something. The strangeness is not a problem waiting to be solved. The strangeness is the answer, and learning to work with the strangeness, learning to compute with it, to build with it, to think with it. That is what quantum mechanics is actually about. Which brings me to the story I really wanted to tell you. The year is 1981. The place is MIT. I have been invited to give a talk at a conference on the physics of computation, on the relationship between the laws of physics and the possibilities and limitations of computing machines. And I am going to stand up in front of a room full of very smart people and tell them something that at first sounds almost childishly simple, and then, if they're really paying attention, starts to feel like the ground shifting under their feet. The question I asked was this: can we simulate nature on a computer? Seems simple, right? Of course we can simulate things on computers. We simulate weather, we simulate atomic explosions, we simulate the folding of proteins. That's what computers are for, simulation. But here's the thing. When I ask, can we simulate nature, I wasn't asking about big things. I wasn't asking about weather systems or orbiting planets. I was asking about the small things, the quantum things, the actual atoms and electrons and photons that make up everything else. Can we take a quantum system, say a molecule of 50 or 100 atoms, and simulate its behavior exactly on a classical computer? And the answer, when I worked it out, was devastating. No, we cannot. Not because our computers are too slow, not because we need more memory, because the nature of the problem makes it impossible for any classical computer, no matter how powerful, to simulate even a moderately complex quantum system. Exactly. Let me explain why. Because this is the heart of everything. And I want to explain it in a way that doesn't require you to know any mathematics at all. Because the insight doesn't live in the math. The insight lives in a simple question about size. Imagine you have a system of particles. Let's say you have one particle. One particle can be in, let's say, two possible states: spin up or spin down, to use the quantum terminology. Fine. To describe that particle's quantum state, you need to track two numbers, the probability amplitude for each of those two states. Manageable. Now add a second particle, two particles each with two states. But in quantum mechanics, the combined system of two particles doesn't have four states, described by four numbers. It has four states, yes, but those states can be combined in any mixture, and the combinations can be entangled, meaning the state of the two particles together cannot be separated into the state of particle 1 and the state of particle 2. They form a unified quantum system. You need four numbers to describe it. Still manageable. Now add a third particle. You need 8 numbers. Add a fourth. 16 numbers. Add a 10th particle. You need over 1,000 numbers. Add a 50th particle. You need 2 to the power of 50 numbers. That's over a quadrillion numbers. A million billion. To describe just 50 particles. Now, there are drugs that interact with proteins in your body. Those proteins are molecules made of hundreds or thousands of atoms. To simulate a single drug-protein interaction exactly, to predict whether a new drug molecule will fold around a particular protein in a way that would make it effective at curing a disease, you would need a classical computer with more memory than there are atoms in the observable universe. Not in the Milky Way, in the entire observable universe. That is the wall, not a temporary wall, not a wall we can engineer our way through. A fundamental wall, built not from engineering limitations, but from the mathematical structure of quantum mechanics itself. Classical computers cannot simulate quantum systems exactly, because classical computers are at their core built from the same discrete, deterministic, non-quantum logic that Planck's beads exploded in 1900. They are, in the most profound sense, the wrong tool for the job. I stood in front of that room at MIT, and I said the only way to simulate quantum mechanics efficiently is with a quantum machine, a machine that itself operates according to quantum principles, a machine that doesn't translate the quantum system into classical bits, ones and zeros, but instead holds the quantum system in its natural state, lets it evolve naturally, and reads out the answer at the end. That was the birth of the idea of the quantum computer, not from engineering ambition, not from the desire to factor large numbers faster, though that came later. From a simple, devastating observation about what classical computers fundamentally cannot do. I want to sit with that moment a little longer, because I think there's something in it that goes beyond physics. There's a kind of arrogance, a well-intentioned, even beautiful arrogance, in the classical computing paradigm. The arrogance is this: we can describe everything in ones and zeros. We can take any piece of reality, any situation, any system, and reduce it to a sequence of true or false statements. Everything is at bottom logical. Everything is at bottom binary. This is an incredibly powerful belief. It built the modern world. Every smartphone, every website, every simulation, every database, all of it rests on the bedrock conviction that reality, however complex it appears, can be broken down into discrete logical operations and reassembled without losing anything important. And that conviction is almost entirely correct. For almost everything we care about, it works. The error rate is so small in so many domains that it doesn't matter. But quantum mechanics is the place where the error is not small, where the assumption that things can be reduced to binary is not an approximation. It's a wrong turn, a fundamental misdirection, and the measure of how wrong it is, the astronomical gap between what we need to describe and what any binary system can hold. That gap is the justification for quantum computing. There's something almost poetic about it. We built the most powerful information processing machines in history on the assumption that the universe speaks binary. And then we discovered that the universe speaks something much stranger, much richer, and much more powerful than binary. And quantum computers are our first real attempt to learn to speak the universe's actual language, not to translate it, not to approximate it. To speak it, let me tell you about three words that are the grammar of that language, three words that are the quantum mechanical principles that quantum computers are built from. The first word is superposition. The second word is entanglement. The third word is interference. And I want to teach you these words not as technical vocabulary, but as genuine ideas. Ideas that, once you've understood them, you'll start seeing everywhere. Not just in physics, not just in computers, but in how you make decisions, how you relate to other people, how you sit with uncertainty, how you figure out what's true. Let's start with superposition. You know what a light switch is: on or off, 1 or 0. This is a classical bit, the fundamental unit of classical computing. Everything your phone does, everything your laptop does, everything the internet does is built from billions and billions of these switches, turning on and off at speeds that are genuinely difficult to imagine, but built from the same basic logical principle: true, false, 1, 0, on, off. A qubit, a quantum bit, is different. And the difference is not just a technical difference, it's a philosophical difference. A qubit is not a light switch. A qubit is a spinning coin. When a coin is spinning in the air, it is not heads, it is not tails, it is in a superposition of both. Both possibilities exist, held in a kind of mathematical embrace, until the coin lands and the superposition collapses into a single definite outcome: heads or tails, 1 or 0. Now here's the crucial thing. Here's the thing that transforms this from a cute analogy into a revolution. A quantum computer can do calculations while the coin is still spinning. It can operate on the superposition, on the mathematical combination of both possibilities, before any measurement is made. And this means that when you have 1,000 qubits, each in superposition, each simultaneously holding both 0 and 1, the quantum computer is simultaneously working on 2 to the power of 1,000 different possible inputs, not sequentially, simultaneously in the same moment. 2 to the power of 1,000. I want you to feel that number. It is incomprehensibly, universe-breakingly large. There are approximately 10 to the power of 80 atoms in the observable universe. 2 to the power of 1,000 is vastly, astronomically, incomprehensibly larger than that. And a quantum computer with 1,000 qubits holds that many possibilities in superposition at once, doing arithmetic with all of them, simultaneously in the time it takes to do one calculation. This is what I mean when I say quantum computers are not faster. They are not doing the same thing faster. They are doing a categorically different thing. They are computing in a mathematical space that classical computers cannot even address. Now, I can feel the question forming in your mind. If a quantum computer holds all possible answers simultaneously, why can't it just give you all of them at once? Why do we even need algorithms? What's the point of having a computer that holds all the answers if you can't get all the answers out? And this is where superposition alone is not enough. This is where we need the second word. The second word is entanglement. And entanglement is, I think, the strangest thing I have ever had to explain to another human being. Not because it's complicated, the description is simple enough, but because the description, when you hear it clearly, produces a kind of metaphysical vertigo that I find both deeply uncomfortable and deeply thrilling. When two quantum particles interact in the right way, they become entangled. This means they share a single quantum state. They are no longer two independent systems. They are one system, described by one wave function, separated in space. And here is the strange part. When you measure one particle of an entangled pair and find out its state, the other particle, regardless of where it is, regardless of how far away it is, regardless of whether it's across the room or across the galaxy, instantly, definitively, non-locally takes on a complementary state. Instantly, without any signal passing between them, without any physical mechanism connecting them, without any interaction at all in the classical sense. Einstein called this spooky action at a distance, and he hated it with a scholarly passion that I find deeply relatable. He spent years trying to prove it couldn't be real, that there must be what he called hidden variables, some deeper level of reality where the entangled particles carry pre-existing instructions about what state to be in when measured. He thought entanglement was a sign that quantum mechanics was incomplete, that somewhere underneath the probabilistic weirdness there was a clean deterministic truth we hadn't found yet. John Bell, in the 1960s, figured out a way to test whether hidden variables could explain entanglement. He derived a set of mathematical inequalities, Bell's inequalities, that local hidden variable theories must satisfy. And experiments, first by John Clauser, then by Alain Aspect, and by many, many others since, showed definitively, with the kind of certainty that leaves physicists nowhere to hide, that Bell's inequalities are violated. Hidden variables cannot explain entanglement. The universe, genuinely, verifiably, experimentally, is non-local. Two entangled particles share a connection that transcends the ordinary notion of space. Now, I need to be very precise here, because this is a place where popular explanations go wrong, and I will not go wrong with you. Entanglement does not allow faster than light communication. You cannot use entangled particles to send a message faster than light. When you measure your particle and learn its state, you instantly know what state the distant particle is in. But you cannot control what state your own particle lands in when you measure it. The outcome is random, and so the information you get is random, and random information cannot carry a message. To compare notes, to realize that your measurements are correlated, you need to communicate classically, at the speed of light or slower. Entanglement is not a communication channel. It is a correlation that exists outside of ordinary space-time. In some sense, we don't have a comfortable classical word for. But here's what entanglement is good for, in the context of quantum computing. It allows quantum computers to link the states of multiple qubits in ways that classical computers cannot replicate without exponentially more resources. In an entangled quantum system, the qubits are not independent. They're part of a single joint state. Operations on one affect others. This means a quantum computer can build up and manipulate correlations between qubits that would require astronomical numbers of classical bits to represent. This is a second source of quantum advantage, not just superposition, but entanglement-generated correlations that make the quantum computer's mathematical space qualitatively richer than anything classical bits can describe. And now here is where I want to push into something that I think goes beyond the physics. Because entanglement is not just a property of particles, it's a property of relationships. And there is something about the way entanglement works, something about the way two things that seem separate share a deeper unity, that I have spent a lot of years thinking about in contexts that have nothing to do with subatomic particles. Think about problems, real human problems, the problems of institutions, of cities, of ecosystems, of families. Classical thinking wants to isolate problems, identify the broken component, fix it in isolation, put it back. This is enormously useful. This is the entire tradition of scientific reductionism, and it has given us modern medicine, modern engineering, modern agriculture. The power of isolating variables, fixing things one at a time is real. But there is a class of problem where isolation doesn't work, where the problem you can see is entangled, genuinely, deeply causally entangled, with problems you can't see from where you're standing, where fixing the isolated component doesn't fix the system, because the problem isn't in any one component, it's in the relationship between them, in the correlation that transcends the boundaries you drew for analytic convenience. Climate change is this kind of problem. Poverty is this kind of problem. Mental health, yours, mine, anyone's, is frequently this kind of problem. The thing we call the problem is almost always entangled with things we haven't thought to look at. And the failure to find the entanglement, the failure to ask, what is this connected to that I haven't examined, is responsible for more failed interventions, more wasted effort, more perpetuated suffering than almost any other single error in human problem solving. I'm not saying this as an analogy. I'm saying this as a structural truth. Entangled problems require entangled thinking. They require looking at the system, the whole system, the relationships to correlations, not just the component that's visibly broken. Quantum computers are powerful, partly because they are built to honor entanglement rather than erase it. They work with correlation. They work with connection. And in doing so, they can solve problems that isolationist thinking can't touch. Now, the third word, interference. Interference is borrowed from wave physics, and it's a concept that's actually easier to visualize than either superposition or entanglement. So I want you to relax into it. You've seen interference even if you didn't call it that. If you've ever thrown two stones into a still pond and watched the ripples meet, you've seen interference. Where two wave crests meet, they add together. The water goes higher. This is constructive interference. Where a crest meets a trough, they cancel. The water goes flat. This is destructive interference. Quantum mechanics uses interference in the same way. The wave function I described earlier, the mathematical description of a particle's quantum state, is a genuine wave in an abstract mathematical space. And like all waves, it interferes. Two quantum paths to the same outcome can constructively interfere, making that outcome more probable. Or they can destructively interfere, making that outcome less probable, even zero. And here is the profound thing. Quantum algorithms, the algorithms that run on quantum computers, are designed deliberately and with great mathematical care to set up interference patterns. They arrange the calculation so that the wrong answers interfere destructively with each other and cancel out, and the right answer interferes constructively with itself and amplifies. By the time you measure the quantum computer's output, the noise is cancelled and the signal has grown louder. And what you read out, with high probability, is the answer you were looking for. This is not magic. This is extraordinary precision. Designing a quantum algorithm is the art of constructing the right interference pattern, of folding the quantum wave function in just the right way so that when the superposition collapses, when the coin lands, it lands on the right answer far more often than chance would predict. Shor's algorithm, which can factor enormous numbers exponentially faster than any classical algorithm, works this way. Grover's algorithm, which can search an unsorted database quadratically faster than classical search, works this way. The algorithms that will one day simulate protein folding, design new materials, optimize supply chains, model climate systems at unprecedented fidelity, all of them work by engineering interference. What I want you to hear in this, what I want to land in you the way it landed in me, is the elegance. There is a particular kind of beauty in a solution that works not by trying all the wrong answers and discarding them, but by building a mathematical structure in which the wrong answers cancel themselves, by making truth louder through geometry rather than brute force. I've spent a lot of time thinking about what the human equivalent of this might be, and I think it's wisdom. Not intelligence. Intelligence can be brute force, it can be running through all the options very quickly. Wisdom is different. Wisdom is knowing how to build the conditions, the mental habits, the values, the questions you ask first, such that good thinking becomes more likely, such that clarity amplifies and confusion cancels. It doesn't happen by trying every possible answer. It happens by shaping the landscape so that the answer has room to emerge. We'll come back to this in a moment. But first I want to bring these three principles together: superposition, entanglement, interference, and show you where they point. Because individually each of them is fascinating. Together they constitute something that I think is one of the most important engineering ideas in human history. And the reason I say that isn't because quantum computers are impressive, it's because of the specific problems they're going to solve. Because those problems, the ones that only quantum computers can touch, are not abstract, they are not academic exercises, they are the actual crisis problems of our species. Let me tell you about one of them. Let me tell you about molecular simulation. Right now, somewhere in a laboratory, many laboratories, hundreds of laboratories around the world, there are scientists trying to design a drug that will treat Alzheimer's disease. They have been trying for decades. They keep failing, not because they're not smart, not because they're not working hard, but because the problem is fundamentally bone deep hard. Alzheimer's disease involves the misfolding and accumulation of proteins in the brain. To design a drug that prevents this, you need to understand, at the atomic level, how specific protein molecules fold into their three-dimensional shapes. You need to understand how a drug molecule would interact with a misfolded protein, whether it would bind to the protein, and if so, how tightly, and whether that binding would have the desired effect. These are quantum mechanical questions. The folding of proteins, the interaction of atoms and molecules, the energy landscapes that determine whether a chemical reaction happens or doesn't. All of this is governed by quantum mechanics. The electron clouds around atoms, the way bonds form and break, the subtle energetic preferences that determine which shape a protein adopts, all of it lives in quantum space. And quantum space, as I've explained, is inaccessible to classical computers at any scale of practical interest. The number of quantum states that need to be tracked to simulate even a moderately large protein exactly exceeds what any conceivable classical computing infrastructure could hold. We can make approximations. We do make approximations. And our approximations are getting better. But approximations are not good enough when the difference between a drug that works and a drug that doesn't work might be a subtle quantum mechanical interaction that our approximation threw away. Quantum computers, true, fully error-corrected quantum computers with enough qubits, can simulate molecular quantum systems exactly, not approximately, exactly, because they operate in the same mathematical space as the molecules they're simulating, because they speak the same language as the problem. This is what I mean when I say quantum computers are not just faster. A quantum simulation of a protein folding doesn't beat a classical simulation of protein folding the way a faster car beats a slower car. It solves a problem that a classical simulation genuinely, fundamentally cannot solve at all. And Alzheimer's is just one example. Drug discovery in general. Designing new catalysts for industrial chemistry. Processes that currently consume enormous amounts of energy could be made vastly more efficient with better catalysts. And designing those catalysts is a quantum mechanical problem. Designing materials with specific quantum properties, superconductors, new battery materials, materials for more efficient solar cells. Modeling the quantum chemistry of nitrogen fixation, the process by which the Haber-Bosch process makes fertilizer, a process that consumes something like 2% of the world's total energy output, could potentially be made enormously more efficient if we could simulate it exactly at the quantum level. These are not science fiction scenarios. These are the stated goals of the quantum computing research programs at Google, IBM, Microsoft, and dozens of other institutions. And while fully error-corrected quantum computers with the kind of qubit counts required for these simulations is still years away, and I won't lie to you about that timeline, it's genuinely hard. The trajectory is clear. The physics works. The principles are sound. The question is purely engineering. And then there's the other thing, the thing that makes governments nervous, the thing that makes cryptographers lose sleep: encryption. The encryption that protects your bank account, your private messages, your medical records, your government's classified communications. The encryption that underlies the trust infrastructure of the entire internet is in many cases based on a simple mathematical fact that multiplying two large prime numbers together is easy, but factoring the result back into its prime components is for large enough numbers computationally impossible for any classical computer in any reasonable amount of time. This is RSA encryption, and it works because factoring is hard. If I give you the number 15, you can figure out that it's 3 times 5 pretty quickly. But if I give you a number that's 400 digits long, the best classical algorithms known would take longer than the current age of the universe to factor it. This is not a soft impossibility. It's a hard one, backed by decades of mathematical analysis. Peter Shor, in 1994, discovered that a quantum computer running what is now called Shor's algorithm could factor that 400-digit number in polynomial time. Not in the age of the universe. In hours. Maybe less, with a powerful enough machine. This is not a marginal improvement. This is the cryptographic equivalent of discovering that the vault you thought was impenetrable has a door. Shor's algorithm, on a sufficiently powerful quantum computer, breaks RSA encryption. It breaks elliptic curve cryptography. It potentially breaks the encryption protecting most of the sensitive digital information in the world. I want to be careful here because this is a place where panic is not the appropriate response. Sufficiently powerful quantum computers, the kind that could run Shor's algorithm on operationally relevant key sizes, do not yet exist. The largest quantum computers today have thousands of physical qubits, but the noise in those qubits, what we call decoherence, the tendency of quantum states to be disrupted by their environment, means that the number of useful error-corrected logical qubits is far smaller. Running Shor's algorithm on a large RSA key would require something on the order of millions of physical qubits, arranged in a fault-tolerant way. We are not there yet. But the National Institute of Standards and Technology, NIST, is already standardizing post-quantum cryptographic algorithms. Algorithms that are hard for both classical and quantum computers to break. The transition is in motion, and the reason I mention this is not to alarm you. It's to make a different point. The point is that this technology is not theoretical. It is not a distant dream. It is an engineering project with a reasonably clear roadmap, being pursued with billions of dollars of investment and the concentrated intelligence of some of the best minds in the world. The physics is done. The question is implementation. And implementation problems, unlike physics problems, tend to yield to persistent engineering, which means the time to understand this, to develop genuine intuitions about what quantum computing is, what it can do, what it cannot do, and what choices we collectively need to make about how it's developed and deployed, is now. Not when the first cryptographically relevant quantum computer comes online. Now, and this is where I want to shift, because I've been talking about physics and machines and problems, and all of that is real and important. But I think there's a deeper conversation available here. A conversation about what quantum mechanics, as a philosophical framework, as a description of what reality actually is, might have to teach us about how to live, how to think, how to hold uncertainty. I told you at the beginning that I wanted to give you something practical, something you could carry out of this conversation. And I think the most practical thing I can give you, more practical than any specific knowledge about qubits or algorithms, is the epistemological permission that quantum mechanics offers. Here is what I mean. We live in a culture that treats certainty as a virtue, that treats knowing definitively, confidently, without qualification, as the goal of thinking. We are rewarded, professionally and socially, for having answers, for being decisive, for projecting confidence. We are punished, in ways subtle and not so subtle, for saying I don't know, for saying both of these things seem true, for saying I'm holding multiple possibilities simultaneously and I haven't decided yet. And quantum mechanics says, but that's how the universe works. At the most fundamental level of reality, the universe holds multiple possibilities simultaneously. It doesn't collapse into a definite state until forced to by measurement. And the act of collapsing it, the act of measuring, changes it. Knowledge is not passive. Measurement is not neutral. The act of demanding a definite answer from an indefinite system has costs. I'm not saying this as a justification for endless indecision. I'm saying this as an observation about the structure of reality that has implications for how we should think about knowledge and certainty. The universe was designed, if design is the right word, and it probably isn't, but let me use it loosely. The universe was arranged such that superposition is not a bug. It's not a deficiency. It's the most powerful computational resource in nature. And maybe, the human capacity to hold multiple possibilities simultaneously before collapsing them into a decision is not indecisiveness. Maybe it's a feature. Maybe the ability to sit with the spinning coin, to let it spin long enough that all the possibilities have interacted, have interfered constructively and destructively, until the answer that amplifies out is wiser than any answer you could have forced by measuring too soon. Maybe that capacity is not weakness. Maybe it's the human equivalent of quantum computation. I'm aware that this can be used to justify procrastination. I'm aware that sometimes you just need to decide. I'm not advocating paralysis, but I am advocating, gently, seriously, a different relationship to the discomfort of not knowing, a different relationship to the period of deliberation before a decision, an understanding that this period is not empty. It is where the computation is happening. It is where the wave function is evolving. Interrupting it prematurely because you're anxious about the uncertainty costs you something. It costs you the answer that a little more time would have made obvious. Let me say something about entanglement and human problems, because I said earlier that I'd come back to this, and I want to make good on that. Most of the problems we face, individually, institutionally, socially, that seem intractable, that seem to resist every intervention, that keep coming back in slightly different forms no matter what we do, are entangled problems. They are problems where the presenting issue is not the actual problem, where what you can see is correlated with, deeply, structurally, causally correlated with, something you can't see from the angle you're looking from. Here's an example. Suppose someone comes to you and says, I can't sleep. I've tried everything. I take melatonin. I go to bed at the same time every night. I don't look at screens. I've read all the advice and I follow it. And I still can't sleep. A classical approach to this problem looks at the component that's broken. Sleep. It tries to fix sleep. More melatonin. Different pillows. White noise machines. Sleep restriction therapy. And sometimes this works, but often it doesn't, because sleep is entangled. Sleep is entangled with workload, which is entangled with workload, which is entangled with a relationship to one's own adequacy, which is entangled with childhood experiences around performance and failure, which is entangled with grief or with physical health or with a dozen other things that have nothing to do with what time you go to bed. The person who can't sleep doesn't have a sleep problem. They have an entangled life, and sleep is the qubit whose measurement result is showing the entanglement. Fixing the sleep qubit in isolation is like performing surgery on a symptom. It might help a little. It might not help at all. The only real fix is to find the entanglement, to identify what this is actually correlated with, and work at that level. I admit, going quite far from quantum mechanics here. But I think the principle is genuine. The most powerful insights tend to transfer across domains, and entanglement is one of the most powerful insights in the history of physics. The idea that two things can share a state in a way that means you cannot understand either one in isolation, that idea has application well beyond subatomic particles. And interference, the quantum principle that says wrong answers cancel each other out and right answers amplify when you design the system correctly. In human life, the equivalent is what I'd call designing for clarity, not eliminating noise. Noise is inevitable, not trying to think your way to a conclusion through sheer force. Force can amplify the wrong answers as easily as the right ones, but instead, creating conditions, specific identified conditions in which your best thinking is more likely to emerge, in which signal amplifies and noise cancels. For me, this was a very particular kind of boredom, not the anxious boredom of having nothing to do, the open, almost meditative boredom of sitting with a problem without any agenda about when to solve it. Playing bongos, walking, sitting in a bathtub, allegedly. Many of my best physical insights came in states that were, from the outside, entirely unproductive. This wasn't accident. This was, I now believe, interference at work. The conditions were arranged so that the noise of my ordinary anxious, effortful thinking died down, and the signal, the actual answer, the thing the mathematics had been pointing to, had space to get loud. Different people have different interference conditions. The practice of finding yours, of identifying what environment, what state of mind, what set of questions produces your clearest thinking, is one of the most high leverage things you can do. Not because it will make you think harder, because it will make the thinking that emerges better, clearer, more likely to be true. And now I want to come to the deepest thing, the thing underneath everything else I've said today. The thing that quantum mechanics, not as a technology but as a description of reality, has to teach us about the nature of knowledge itself. The deepest lesson of quantum mechanics is not about particles. It's not about waves. It's not even about uncertainty. Exactly, though, uncertainty is part of it. The deepest lesson is this. The universe is not obligated to be understandable. It is only obligated to be. Let me stay with this for a moment because I think it's more radical than it sounds. We tend to assume, I think most of us assume this without ever consciously articulating it, that if something is real, it should in principle be understandable. That reality and comprehensibility are linked, that if we think hard enough, with the right tools, with enough data, we can eventually arrive at a picture of how things work that satisfies our intuition. A picture we can hold in our heads. A picture that makes sense in the way that stories make sense, where the cause leads to the effect, and the plot has a logic. Quantum mechanics breaks this assumption. Not gently and not partially. Definitively, there is no interpretation of quantum mechanics. Not the Copenhagen interpretation, not the many worlds interpretation, not Bohmian mechanics, not any of the dozen serious attempts physicists have made to provide a satisfying mental picture that is both consistent with experiment and intuitively comfortable. They all preserve the mathematical formalism because the formalism works, but none of them gives you a picture you can see in your head without something being wrong. Either the wave function is not real and measurement creates reality, which raises questions about what counts as a measurement, or the wave function is real and every quantum measurement splits the universe into branches, which is extraordinary even by the generous standards of extraordinary. Or there are hidden variables guiding particles, but they're non-local in a way that still doesn't help your intuition. There is no option C where it all makes sense in the way that a steam engine makes sense. And I have spent a long time, literally decades, learning to be comfortable with this. To recognize that my discomfort is not a sign that I'm missing something. My discomfort is a correct response to the actual structure of the territory. The map will never be the territory here. The story will never capture the thing. The math works. The experiments confirm it. The technology built on it functions exactly as predicted, and yet the mental picture remains elusive, permanently, by design. Here is what this means for how you live. You are asking questions, some of you, many of you, that don't have clean answers. Questions about who you are, what you should do with your life, how to navigate a relationship that defies simple description, how to grieve something that isn't neatly grievable, how to build something when you can't see clearly what you're building toward. And there's a part of you that is waiting, genuinely waiting, holding your breath, for the answer that will feel satisfying, the answer that will fit in a sentence, the answer that will resolve the uncertainty the way a detective story resolves at the end, with all the pieces clicking into place. Quantum mechanics, if you take it seriously as a description of reality and not just as a technology, gives you permission to stop waiting for that, not because the answer is unknowable, but because reality itself at its deepest level operates according to truths that don't resolve into comfortable mental pictures. And the fact that you're still functioning, still asking questions, still making decisions and building things and loving people, despite not having resolved those deep uncertainties, that's not evidence that you're failing. That's what living in a quantum universe looks like from the inside. The universe built its most powerful computational tool out of embraced uncertainty, out of superposition held without collapse, out of entanglement that defies separation, out of interference that makes truth louder without forcing it. And the quantum computer is in this sense not just a machine, it's a philosophical statement. It says we finally made peace with the universe's actual grammar. We finally stopped insisting that reality speak binary. We finally agreed to meet nature where it is, rather than demanding it come to us. I find that moving. I find it genuinely, unexpectedly moving. Not in a sentimental way. I'm not a sentimental person, I don't think. But in the way that precision is moving. In the way that an experiment that confirms the strangest prediction of the strangest theory is moving. There's something about this particular act of intellectual humility, this specific decision to build machines that speak the universe's actual language, rather than forcing the universe to speak ours, that feels important beyond its technological implications. And I want to give you something to do with all of this, because we've covered a lot of territory today. We've gone from the crisis of classical physics, to Planck's quanta, to quantum mechanics, to the wall of classical computers, hit to the principles of quantum computing, to the problems those computers will solve. And I don't want to leave you with just understanding. I want to leave you with practice. The first practice I want to give you comes from superposition. And it's this: hold the question longer. Most of us, when facing a significant decision, collapse the superposition as fast as we can. We decide. We commit. We stop being uncertain, because uncertainty is uncomfortable. And certainty, even wrong certainty, feels better than the spinning coin. And the cost of this is that we arrive at answers that are fast but not wise, answers that escape the discomfort of uncertainty rather than emerging from honest deliberation. The practice is simple and it's hard. When you face an important decision, before you decide, write down every possible answer, including ones that contradict each other, including ones that seem wrong, including ones that feel uncomfortable. Hold them all simultaneously. Give them time to interact. Let them interfere with each other. Notice which possibilities grow stronger as you sit with them, and which ones cancel, and then, only then, decide. This is not a recipe for paralysis. This is a recipe for wisdom rather than haste. And the amount of time required is smaller than you think. Often, just one additional day of holding the superposition produces a qualitatively better answer than the one you would have forced immediately. The second practice comes from entanglement, and it's this: look for the hidden correlation. When you have a problem that isn't yielding, a problem that you've tried to fix and it keeps coming back, or that feels stuck in a way that effort doesn't seem to help, stop trying to fix the presenting problem. Instead, draw it at the center of a page and draw lines outward to every other domain of your life it might be connected to. Work, relationships, health, meaning, identity, history, and then look for correlations. Look for the places where when one thing moves, this thing moves. The entangled root of an intractable problem is almost always in a domain we haven't examined, not in the problem itself. This requires honesty. It requires looking at things you might prefer not to look at. Entanglement in quantum mechanics is not something you can opt out of. Once two particles share a state, they share it regardless of whether you find the arrangement convenient. The same is often true of entangled human problems. The correlation is there whether or not you choose to see it. The third practice comes from interference, and it's this: design for your own signal, identify as specifically as you can the conditions under which your clearest thinking emerges. Not your most productive conditions, not the conditions under which you generate the most output, the conditions under which you are most likely to be right, most likely to generate the insight that actually matters. For some people, this is early morning. For some, it's long walks. For some, it's a specific kind of conversation with a specific kind of person. For some, it's writing in a particular place. Whatever it is for you, protect 1 hour this week for exactly that condition. And observe what surfaces, not what you produce, what surfaces, what emerges without being forced. The fourth practice is about specificity, about using the right tool for the territory. Quantum computers are not universally superior to classical computers. They're precisely suited to a specific class of problems, and for everything else, classical computers are better. The analogy for human thinking is real. We have different modes, different capabilities, different ways of processing, and a lot of suffering comes from applying the wrong mode to the wrong problem. Logic applied to grief, efficiency applied to love, speed applied to understanding. These are mismatches. They feel like failure. Why can't I think my way out of this grief? Why isn't trying harder working? But they're not failures of effort. They're category errors. The practice is to name the mode you're overusing and honestly ask, is this the right tool for this territory? And if it isn't, what would the right tool be? The fifth practice, and the most important one, is this: engage with the unanswerable. Find one question you've been carrying about yourself, your life, your purpose, your past, that you haven't answered. A question you've been waiting to resolve before moving forward. And write down, honestly and specifically, what you would do, how you would live, who you would become, how you would engage. If you gave yourself permission to move forward without resolving it first, then do one of those things. Today. Not because you've answered the question, because the universe has shown us at its deepest level that engagement doesn't require certainty. They hold superpositions rather than collapsing them prematurely. They use entanglement rather than demanding separation. They design for interference rather than fighting noise. And they produce extraordinary results, results that no classical system can match, because they've agreed to work with reality rather than against it. You can do the same. You don't need to resolve the uncertainty to live fully inside it. So let me close by bringing this back to where we started, because I asked you a question at the beginning, and I want to answer it now. I asked, what if the universe isn't computing the world the way we assumed? What if it's doing something far weirder, far more beautiful, and far more terrifying than any machine we've ever built? Here's the answer. It is. The universe is doing something far weirder and far more beautiful than any classical description can capture. At the level of individual particles, at the level of electrons and photons and the quantum fields that underlie them, reality operates according to principles that have no analog in ordinary human experience. Superposition, entanglement, interference, measurement-dependent reality, irreducible randomness, non-locality. These are not approximations, not models, not useful fictions. They are the actual structure of the actual universe, confirmed by the most precise experiments in the history of science. And for most of human history, we couldn't do anything with this knowledge except be confused and astonished by it. We could write down the equations, we could confirm the predictions, we could shake our heads at the philosophical implications, but we couldn't harness it, we couldn't build with it. We couldn't use the universe's actual grammar to do useful work. The quantum computer is the moment we could. The moment we built a machine that doesn't translate quantum reality into classical terms before processing it. That holds the quantum state, lets it evolve according to quantum rules, and reads out the answer. That moment, that specific engineering breakthrough, is not just a technological milestone, it is a philosophical one. It is the moment we stopped demanding that the universe speak our language and started learning to speak its. And here is what that means for you, for the one person I've been talking to this whole time. The curious person who sat with us for 40 minutes, who followed me through history and physics and philosophy and practice. Here is what I want you to take from today. You are not confused because you're not smart enough. You're confused because reality is genuinely this strange. The strangeness you feel when you try to understand quantum mechanics is not a gap in your comprehension. It's an accurate response to the actual structure of existence. The greatest physicists in history felt the same strangeness. They didn't resolve it. They learned to work with it. And working with it, they built the most powerful and beautiful scientific framework humanity has ever produced. And the questions you can't answer about your life, your purpose, your relationships, your future, those questions are not evidence of your failure to understand yourself. They may be evidence that you are complex in the way that quantum systems are complex, that you contain more than any single measurement can capture, that you are in superposition, multiple things simultaneously, and that collapsing yourself too soon into a single definitive identity cost you the computational richness of everything else you could be. The universe did not become less real when we discovered it was quantum mechanical. It became more real, more strange, more beautiful, more capable of surprise. And you, sitting with your uncertainty, holding your questions, looking for the entangled root of your intractable problems, designing the interference conditions under which your best thinking amplifies. You are not broken. You have not been doing it wrong. You've just been using a classical description for a quantum life. Quantum computers don't break physics. They finally tell the truth about it. And maybe that's available to us too. The chance to finally tell the truth about the uncertainty we've been carrying. The chance to stop pretending we have it all figured out. The chance to work with reality's actual grammar instead of the comfortable fiction we substituted for it. The universe built its most powerful tool from embraced uncertainty, from superposition held with courage, from interference that makes truth louder without forcing it. You have all of those capacities. You've always had them. You just needed permission to use them. That's what I wanted to give you today. If something in this landed, if one moment shifted something in you, or opened a question you hadn't thought to ask, or gave you language for something you felt but couldn't name, I'd genuinely love to know what it was. Leave it in the comments. Not because I need the engagement, because the ideas deserve more room. Because conversations that start in comments have a way of becoming the most interesting conversations of all. And if you know someone who is waiting for certainty before they begin, who is holding their breath for the answer that will make everything clear before they allow themselves to move forward, share this with them. Not as a lecture, as a hand extended, as a reminder that the universe itself computes in uncertainty. And look what it built. There's more where this came from. More physics, more philosophy, more strange and beautiful territory to cover. If you want to keep going, subscribe, and we'll keep going together. Until then, keep asking the questions that don't have clean answers. Sit with the spinning coin a little longer. Look for the entanglement you haven't found yet. Design conditions where your truth can get loud. That's where everything interesting lives. And that's where I'll see you next.